We're going to look at applications with rates of change and see the many things in the world that can be modeled by looking at their rates of change in some of the many disciplines. First of all, we want to get this idea again. If we have a secant line that joins up the points P and Q and we compute its slope, it's the change in y over the change in x, and that would give us the average rate of change of the function between x1 and x2 in this case from P to Q. And then we know as we let delta x get smaller and smaller and smaller so that we can approach P if we had limit as delta x approach 0 of this average rate of change, so that then this was smaller and smaller, we would have the derivative, and that would give us the instantaneous rate of change, tell us what was going on at that instant. First of all, we're going to look at an example in physics, and we're going to consider horizontal motion. Here we have little guy riding a cart here, and we're going to see how he moves horizontally back and forth, and this graph right here is showing us what his velocity does. We see that he's increasing in velocity, then he's going to keep a constant velocity, then his velocity is going to decrease, and right here at 3 it's going to be 0. Then the velocity is going to go negative, and then still negative at 5. The velocity is going to be 0 and remain that way until 6, and then the velocity is going to increase again. So let's put this little guy in action and see what that shows us motion wise. So he was moving along, he kept moving, he just didn't speed up any here. Slowed down at 3 seconds, there was that little pause, went in the other direction, moved off to the left here. That's what the negative velocity meant. Just sat there from 5 to 6 because the velocity was 0, and then started to increase again. So we could actually see him with his position here and see that he moved along, not speeding up but still moving there. 0 right at 3, went the other direction. He went too fast for me to keep up with. I'm going to have a link to this after so you can go play with it and see it in action if you would like. Now let's think about what was going on with the acceleration. Speeding up here at a constant rate because the slope of this line, this is a line, it's not a curve, it's a straight line. Whatever its slope is then would be its acceleration, how fast it was speeding up. Constant velocity here, so the acceleration would be 0. Slowing down here, this curve is decreasing. The acceleration here would be negative. Okay, then we are going in the opposite direction here because the velocity is negative, but we can see that this curve is still decreasing. Then it's increasing here, right here when the velocity is 0. If it's sitting there, there would be no acceleration. And then velocity starts increasing at a constant rate again, so whatever the slope of this line is would be the acceleration on that interval. So let's go ahead and see this. So this is what we saw. Constant acceleration of 10 because the slope of this is 10. Staying at a constant velocity here, so no acceleration. Okay, decreasing here, so the acceleration is negative but getting slower and slower here, so acceleration negative but getting towards 0. Sitting at that instant at 3, no acceleration either. Still now decreasing, and so this acceleration is negative, but the magnitude of the acceleration is becoming larger because the absolute value of this point is larger than here. So we see that the velocity is increasing but in the negative direction. So think of those negative signs as why this is a negative here. And then going towards 0 again. And as we get to 5, we're sitting there, so there's no acceleration. Then we start to apply some velocity but at a constant rate, and therefore the acceleration is constant there. So let's go ahead and look at a problem using this idea. The position of a particle is given by the equation S of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is in meters. Find the velocity function. Velocity is the rate of change of position. So how many meters is he changing in how many seconds? So what I want to do if I want a velocity function is I want the first derivative of position. That's going to give me 3t squared minus 12t plus 9. What is the velocity at 2 seconds? So I'm going to put that right here. I just need v of 2, so that means put a 2 in that function that I just found for velocity. That looks like that's going to be 12 minus 24 plus 9. So negative 12 plus 9, negative 3, putting the units on meters per second. So what does that tell me about the motion of this particle? It tells me that at 2 seconds it is moving, we'll say left and right, positive and negative. I get a negative velocity. It's moving off to the left at 3 meters per second. Let's find the velocity at 4 seconds. So we'll just go ahead and put a 4 in our velocity function. And it looks like I've got 28 minus 48 plus 9, so 9 meters per second. So this tells me it has turned around and gone the other way, and at 4 seconds it is moving along to the right at 9 meters per second. When is the particle at rest? At rest would be it has no velocity. So I would take the velocity function and figure out when it was 0. Okay, there's a 3 and everything. T squared minus 4t plus 3. I'm interested in where that equals 0. And that's t minus 3, t minus 1. So t equal 1 or 3 seconds. So at t equal 1 or 3 seconds, this particle is not moving. When is the particle moving backwards? So the negative direction, or going off to the left. Well, this graph, if I'm looking at my velocity function, is going to be a parabola that opens up. So I'm going to do a quick sketch to answer this question. I just found the intercepts of this parabola. They were 1 and 3. And so I could do a quick sketch of this parabola. I don't need it any more accurate than that, because now I could answer the question of when it was moving, velocity is positive, that would be these upper pieces, and when the velocity is negative, that would be this lower piece there. And when we put 2 in, we got a negative velocity. When we put 4 in, we got a positive velocity. So when is this particle moving in the negative direction? That would be from 1 to 3 seconds, because we just graphed that velocity function and we got a negative there. This is actually showing what this is doing then, and it's actually horizontal motion right here along this line, but they've put it above so it's not moving up, but so that it wasn't over the top of each other so you could see. From 0 to 1 second it was going forwards, then from 1 to 3 it was going in the negative direction, and then after 3 it was moving back again in the positive direction. Okay, this is still the same particle. Find the total distance traveled in the first 5 seconds. So it went back over the top of each other. If we go back and look at this picture, so I don't want to look at where it is at 5 seconds, because that would give me its position here, but it would just tell me how far it was from here to wherever it ended up in 5 seconds. It wouldn't tell me how far it traveled, because it went this way, then it went back, and then it went this way again. So what I'm going to need to do is figure out how far it is to get to 5, and that would tell me how far it went right here, but then I need to figure out how far it went in the first 1 second and add that on, and then I could actually double that because it went back in the next from 1 to 3 seconds. So the distance it traveled is actually this piece plus this piece plus this piece. And this piece I could find by figuring out its position in 5 seconds. This piece I could find by figuring out its position in 1 second, and then I could double it to get number 2's piece. So let's do that. So let's go ahead and see the position in 5 seconds. And that's going to be 125 minus 150 plus 45. So that's going to be 20 meters. So that's where he ends up, and traveled 20 meters there. But let's figure out the distance in 1 second. And that's going to be 4. So that's when he started here and went 4, and then he doubled around and went back 4 again. So our total distance, 20 plus 4 plus 4, so that's going to be 28 meters for our total distance traveled. Find the acceleration. Well, the acceleration is how much the velocity is changing. So if we want acceleration, it's going to be the derivative of velocity, and it's going to be then the second derivative of position. So we had our velocity function previously. So our velocity was 3t squared minus 12t plus 9. So our derivative of that, which would be our acceleration, is going to be 6t minus 12. What's the acceleration at 4 seconds? So our acceleration at 4 would just be putting a 4 in that acceleration function we just found, and that looks like that's going to be 12, and our units are meters per second squared. When is the particle slowing down? So if we want to know when it's slowing down, if it was going forwards, then the acceleration is negative, then it's going to be slowing down. But if it's going in the negative direction and acceleration is negative, then that's going to combine and make it speeding up. So I'm going to need to look at the interaction of the two. It's not going to simply be when the acceleration is negative. So we had our acceleration function, which was 6t minus 12. That's just a line. And so I know that at t equal 2, anything where t is greater than 2, I'm going to get a positive for the acceleration function, and anywhere where the t is less than 2, I'm going to get a negative. So I'm going to need to look at these, and maybe a graph would be the easiest way to kind of see this. We have the acceleration function, which was at 2, it went positive. It was negative before that. Here's our position function. Our velocity function was our parabola here, and it was negative. The particle was going backward from 1 to 3. And this kind of shows us the forward-backward things, but what we're now looking for is when this acceleration has the opposite sign of the velocity, then it means it is slowing down, and that's what we wanted to answer. We see right here acceleration is negative, velocity is positive, so this would be slowing down. Now the acceleration is still negative in here, but so is the velocity, so it means it's actually speeding up because they're working in the same direction. But we see that right here the velocity is still negative, but the acceleration now goes positive, and they have opposite signs, and so it is slowing down. And then right here, once the velocity goes positive, the acceleration is also going positive, then it is speeding up again. Here is an animation you will have a link to after this video as well, and you can kind of look at the interaction between the position, the velocity, and the acceleration. This also shows the total distance traveled. Right here you can mess around with, you can choose if you want polynomial or a trig function, and you can mess around with the parameters so that you can affect the graph, and then you can watch what goes on as this particle follows this position function and what its velocity is doing and what its acceleration is doing.